Jai Jagannath. So, welcome to More Physics. Today, this is lecture number 3 of chapter 25, that is current, resistance, and EMF. So, we will discuss now what is the physical concept of EMF. So, what is the circuit? What is EMF? Now, see, EMF means suppose you take a conductor. This is a conductor. So, this conductor, this terminal is A. Let us say this terminal is B. So here, let us say at any instant, I established an electric field of what? Of electric field of E1 inside the conductor. So what will happen? Due to this electric field, and this is which type of conductor? This is isolated conductor. This is isolated conductor. It is not connected to any other circuit, any other parameter. Okay. So now, if an electric field of E1 is established in this isolated conductor, what will happen? So, and let us say this conductor resistivity is rho. Resistivity is rho. So, what will happen? Due to this electric field, all the positive charge inside the conductor will accumulate in this end, B end. Because when any charge particle is brought inside an conductor or inside an electric field, those charge particle will experience force, and if the charge particle is positive, positive charge will move along the direction of electric field, and all the negative charge will move opposite to that of electric field. So now what will happen? After some time, some positive charge will accumulate at B, negative charge will accumulate at A. So due to this positive and negative charge, what will happen? An electric field will be developed in this direction, because this is positive charge, this is negative charge. Due to positive and negative charge, another electric field will be developed, that is say E2. So what will happen? When after very small fraction of second, what will happen? This E1 will be equal to E2. So if E1, so E1 vector is equal to minus E2 vector. So E1 is the external electric field, E2 is the electric field developed in the conductor due to accumulation of positive charge, negative charge at these two ends. So in the fraction of second, we will find the net electric field intensity, which is equal to E1 plus E2 vector. Both are equal and opposite. So net electric field intensity will be 0 inside the conductor. So if net electric field intensity inside the conductor will be 0, we know that J is equal to E upon rho. So J is current density. So E is the electric field. Since electric field is 0, so current density is equal to 0. So current density 0 means current is equal to 0. Current 0 means there is no steady flow of charge. No steady flow of charge. So this is the situation for isolated conductor. Okay. So in this case, finally the charge will stop. So there is no steady motion of the current in this incomplete circuit. So we have to maintain the continuous flow of charge or current. This accumulated charge, that is positive at B end and negative at A end, must be extracted by some source, which says that now you see, so this is the isolated conductor. Now, same conductor, here you see this is A, this is B, and here what was the net current? Net current is 0 due to the total electric field is 0. Now, if I will take some arrangement by which all the positive charge at this B end will be driven out, and all the negative charge also driven out from the A, at that time there is no opposing electric field E2. By this electric field, continuously charge will flow. So to have continuous flow of a charge or current, this accumulated charge, that is positive at B end and negative at A end, must be extracted by using a source. And so if I will use a source, you see this A is connected to this terminal, so this is also A. This B is connected to this terminal, this is also B. So now I will use a source. So that source, so you see, since the initial direction of electric field is from A to B, definitely A is at a higher potential, B is at a lower potential. And here, what is the role of this source? The role of this source is to drive out this positive charge from this end, and or we can say drive out the negative charge from this end. That means this source must send the charge from lower potential to higher potential. You see, this is the lower potential, this is negative side, this is positive side, because we have applied the electric field along this direction, A to B. That means A is positive potential, B is negative potential. So this source must extract the charge from this B end and send this charge to which side? To A side. That means the role of the source is to send the charge from lower potential to higher potential. That is the objective of the source. Okay. So source will send the charge from lower to higher potential end, so that this opposing electric field, that is E2, cannot be produced. So just you see, just like when water falls from certain height, suppose you see, so this is suppose a hill, so here water is falling from the hill to the ground. Okay, so this is only one time. But if I can able to send this water to the uphill position by using what? By using a pump, then a continuous water will flow. That means this pump is raising or lifting the water from low level to high level. So the role of a pump is just like the role of the source, electrical source. So here this source is sending the charge from lower potential to higher potential, so that this opposing electric field will be cancelled and we will get a continuous flow of the current. So this is the role of the source. This is EMF. Okay, so you see this is the conductor and this is a ideal source who will send the charge from lower potential to higher potential. Then what is EMF? EMF is nothing but the source which drives the current, that is drives the positive charge. Flow of positive charge is nothing but the current. So from lower potential to higher potential, that is called source of EMF. So, and from the name, so EMF means what? What is the full form of EMF? It is electromotive force. So that does not mean that EMF it is a force. It is not a force, but it is a energy per unit charge. That means what the energy to carry a unit charge from lower potential to higher potential, that is called EMF. Okay, so it is not a force. From the name it indicates it is a force. No, it is not a force. So it is an energy per unit charge which allows to pass through it, like potential. So what is potential? It is amount of work done by bringing a unit charge. So similarly, the EMF symbol is represented by like this. So this is the EMF symbol. Okay, so this is the EMF symbol, and this EMF is same as potential. EMF is same as potential. Okay, and you know what is potential? What is the unit of potential? Potential unit is joule per coulomb. That is work done per unit charge. So that means the potential unit is joule per coulomb, that is called volt. So unit of EMF is also volt. Okay. Then question comes, what is the source of this EMF? So now source of EMF are of varieties nature. The one may be battery. Okay. Another may be generator, DC generator or AC generator. Or you can say the source may be solar cell or fuel cell, etc. So these are called the source. So what is the principle of source? Source, everything. You see, positive charge flows from along the direction of the electric field. But the source will send the charge from lower potential to higher potential. So by some mechanism. Okay, by some mechanism. So here we are using different types of source, that is battery, generator, solar cell, like this. So here what happens? Suppose we are taking a battery. So this battery converts the chemical energy inside this electrolyte to the electrical energy. Suppose a generator is rotating. So during rotation, that rotation means which energy? Mechanical energy. So that mechanical energy is converted to electrical energy. You have seen in the thermal power plant, and so here heat energy is converted into electrical energy. So in this way, this source will send a charge from lower potential to higher potential, and here charge will move. So charge or current will follow a continuous path, continuous motion, and the circuit on which current flows, that is called electrical circuit. And what is ideal source? What is ideal source? Ideal means there is no loss. So here the ideal source of EMF maintains constant potential difference. Maintain constant potential difference between its terminals. Okay, and it is independent of current. Whatever may be the current, if current magnitude will change, but potential difference across these two terminals always remains same. This is only possible for ideal source. Okay, so what is the mechanism? What is the mechanism of the source? You see, so here A and B terminals of ideal source maintained is, here it is positive, here it is negative. That is, here this is higher potential, this is lower potential. Okay, so this A plate is called anode, this is your anode, and B plate is called cathode. So due to the electric field developed inside this, so here it is positive, here it is negative. So electric field developed is from positive to negative. So what will happen? So this electric field is developed in between the source from left to right, and here this A point is connected to this point, B point is connected to this point. So due to this, so this will be positive, this will be negative. So again electric field will be developed inside the conductor from left to right. That is, outside to the conductor, electric field developed is same as that of the electric field developed inside the source. Suppose you take a charge Q inside the source. So what will happen? So this Q charge will experience a force along the direction of the electric field, and that force is equal to, say, Fe. So what is Fe? Fe is equal to Q into E. So what is the direction of Fe? That is force due to electric field. It is towards right, inside the source. Okay, but the source, inside the source, so this source will provide an additional non-electrostatic force. So this source will provide an additional non-electrostatic force. So that is not electrostatic force, it is called non-electrostatic force. So source will provide a non-electrostatic force on the charge. Okay, so due to this non-electrostatic force provided by the source, this charge will move against to the motion of electric field. That means the force due to electric field is towards right, but this Fn, which is called non-electrostatic force, which is produced by the source, will have this force will move this charge against the direction of the force due to electric field. Okay, so now, so this Fn will try to take this charge from B end to A end. Just like you see, just let me take an example. You see, suppose this is a container, this is another container. So here this level is higher, this level is lower. If I will connect a conductor, what will happen? Water will come from higher side to lower side. Okay, after very fraction of second, if we will not connect a source, after very fraction of second, the level of both will be same and the water flow stops. But if I will make what you see, this is a pond. I will connect a motor. So this motor will push or lift the water from ground level to higher level. So in this way we can get a continuous flow of water. So here this pond is nothing but, this motor in this example is nothing but the source. So that source may be a battery, may be generator, may be solar cell, may be fuel cell. And you see, what is the origin of Fn? How the non-electrostatic force is developed inside the source? It depends upon kind of source. This the force, that is non-electrostatic force, depends upon which type of source you have taken. For generator, you know, it is the force due to magnetic field. In a generator there is a magnetic field, and when charge moves, so a force will be expressed by the moving charge. You know, force experienced by a moving charge is equal to F is equal to Q into V cross B. So if there is a magnetic field and there is a moving charge, then due to that moving charge a force will be developed. So in that case, this force is produced by the source, that is called non-electrostatic force. For battery, if you will use battery or solar cell, it is due to diffusion process and varying the electrolyte concentration resulting from the chemical reaction. So you can follow the principle of battery from chemistry also in details. For ideal source, what is the difference between ideal and practical source? For ideal source, the force due to electric field is equal to force due to non-electrostatic force, but they are in opposite direction. Or you can say the magnitude of the electrostatic force is equal to magnitude of the non-electrostatic force. Both are in opposite direction. So total work done on charge Q is equal to 0 because both are opposite and same magnitude. So total charge, the total work done on charge Q is equal to 0. Just like water comes from A container to B container, I had explained that due to gravitational force, like electric field, the force due to electric field. And same water is lifted from the lower level to higher level due to pump. So that pump will provide which force? Non-electrostatic force. So net work done during the loop is equal to 0. So I can write work done by non-electrostatic force Fn increases potential energy, that is Q times of E is equal to Q times of the potential difference across A and B. So that implied the EMF value is equal to terminal potential difference. Whatever the voltage is developed in the source is equal to potential difference across this A and B terminal. Or you can say the EMF is equal to terminal potential difference. This is for which source? This is for ideal source. This is for ideal source. But potential difference across A and B inside the conductor, if the resistance of the conductor is R, then we can write the potential difference, the terminal potential difference across the conductor is nothing but I into R. Okay. So for ideal source we can write, for ideal source we can write the terminal potential difference VAB is nothing but the EMF, which is equal to I into R. This is for ideal source. This is for ideal source. So another thing is that when positive charge Q flows around the circuit, the potential rise, that is E, inside source is equal to the potential drop VAB, which is equal to I into R, as it passes through the remainder of the circuit. That means the potential rises is equal to E, which is equal to potential drop across the circuit element, that is IR. So, or you can say this IR is equal to VAB. So that means in a closed circuit, the rise in voltage is equal to drop in the voltage in other element, or you can say the sum of EMF source, in circuit is equal to sum of potential drop in the circuit. Now see, the detailed concept of EMF is not necessary for exam point of view. Those who are interested, they can see this video, else you can skip. So now we will start internal resistance. Now we will discuss what is internal resistance. Okay. So you know, when current passes through any body, there is some opposition. If current will pass through my body will also oppose. Similarly, when current will flow from lower potential to higher potential inside the source, let us say inside the battery. So in the battery there is electrolyte solution. So when current passes through the electrolyte solution, that electrolyte solution will also oppose to the flow of current. So that opposing characteristic of the electrolyte solution is named as internal resistance R. So the internal resistance inside the source, inside the EMF source, will oppose to the flow of current. And the internal resistance depends upon which factor? It is directly proportional to the D. So what is D? D is distance of separation. Distance of separation between two plates. Remember, these two plates are of different material. If this is copper, this is aluminum. Or if it is aluminum, it is silver. So both are made up of different materials. So the internal resistance is directly proportional to the distance between two plates, or it is inversely proportional to the area of the plate. If the plate area increases, internal resistance decreases. Also, the internal resistance is directly proportional to the concentration of the electrolyte. Concentration of electrolyte. And it is also inversely proportional to temperature. That means if temperature will increase, internal resistance will decrease. Okay. So when current flows inside the source, due to internal resistance, there is some potential drops. And what is the potential drops? So potential drops inside the cell or inside the source is equal to I into small r. So this is the potential drop inside the source. Then what is the terminal potential difference across A and B? So the terminal potential difference across A and B is equal to the total EMF E. Out of that there is some voltage drop internally. So this is your terminal potential drop. Okay, this VAB is called terminal potential difference. E is called EMF. IR is called internal drop. Which drop? Voltage drop. And this is for which type of source? Practical EMF source. Practical source. But for ideal source, there is no drop. So the terminal potential difference is equal to E. This is for ideal source. There is no internal drop. Okay. So now for we can say for practical source, the terminal potential difference is less than the EMF. For ideal source, the terminal potential difference is equal to E. Suppose, so what is actually terminal potential difference for practical source? What is the difference between V and E? Suppose you will go to market, and in the market you will ask for a shopkeeper, just give me a 1.5 volt battery. 1.5 volt battery. So when you are buying this battery from the shop, you just connect your battery. One is a positive terminal, another is a negative terminal. You connect this battery through a voltmeter, and that voltmeter will show 1.5 volt. So this is your EMF. But when that battery will be used in your torch light, when you will use in the torch light and you just switch on the battery, at that time the light will glow, torch light will glow. And at that time, if you will measure the voltmeter measure the potential difference across the two terminal of the battery, that battery voltage will never get 1.5 volt. It is less than 1.5 volt. Let us say it is 1.3 volt. You are measuring the voltage across this battery is equal to 1.3 volt when it is used or when current passes through it. Then what is the difference in this voltage? 1.5 minus 1.3, that is 0.2 volt. So this 0.2 volt is the internal drop inside the battery. Okay, so this is the terminal potential difference. This is the EMF. Now see, suppose this is a conductor whose resistance is R. This is a battery whose EMF is E, internal resistance is R. So here this circuit is connected through a switch, and you connect. This is your A terminal. This terminal is A, means this terminal is also A, because there is no other electrical parameter. If this is B, this is also B. This is also B. This is also A. This is A. So here this voltmeter will read the voltage across A and B, and this voltmeter will read across A and B. Since both are same, AB and AB, so this voltmeter reading and this voltmeter reading will be same. Okay. Then question comes, what is the voltage across A and B terminal? Let us say current is your I. So current always starts from positive terminal of the battery and enters in the negative terminal of the battery. Inside this battery, direction of the current is from lower potential to higher potential. So here what is the value of VAB? Terminal potential difference. Current in the circuit is I. Resistance of this conductor is R. So VAB is equal to I into R. Okay, VAB is equal to I into R. So now so this is VAB is equal to IR. But when switch is open, the current will be zero. So if current will be zero, then what is the terminal potential difference? We had known the terminal potential difference is equal to E minus IR. So if switch is open, I is zero, so the terminal potential difference is equal to E. Okay, terminal potential difference is equal to E. Similarly, so this is the terminal potential difference, that is VAB is equal to E when the switch is open. But when switch is closed, so what will happen? to the terminal potential difference. So the terminal potential difference will be E minus I into R. So this is the terminal potential difference when switch is closed, and this is the VAB is equal to E. That implies VAB is equal to E when the switch is open. Okay. So now you see. So, but always the terminal potential difference, suppose the switch is closed, the terminal potential difference across this V is equal to I into R. But we know what is V, or you can say VAB. VAB is equal to IR. Here VAB is equal to E minus IR. So that implied I into R plus I into R is equal to E. So that implied I, take common I into R plus R is equal to E. So that implied I is equal to E divided by small r plus R. So this will help when you will solve some numerical. Okay. So now you see, this is your I. Again, V is equal to, V is equal to IR. I is nothing but E by R plus R whole into R. So that is equal to, just cross multiply this. So V is equal to IR. In place of I, you write E by R plus R into R. So this V into R plus V into capital R is equal to E into R. So that implied V into R is equal to, take common R, V minus E into R. Sorry, E minus V. E minus V. That implied small r is equal to E minus V divided by V whole into R. That means this is the method how to find internal resistance. How to find internal resistance of a battery. So first, what you will do? Just connect this. Just take the open switch. Take switch open. Let us say switch is open. Now measure the potential difference across this terminal of the battery. So that will give E. Then close the switch and measure this voltmeter reading. That is V. And using the multimeter, you find the value of external resistance R. So by putting all these value here, we can get the internal resistance. Okay. So another thing, important thing is that for practical purpose, I am telling, if temperature decreases, the internal resistance will increase. If internal resistance will increase, you see, if temperature increases, suppose, if temperature decreases, internal resistance increases, then current will decrease. So this is the case. You have marked when in the winter morning, when you will start your car, that car will not start because the starting current is less in the winter morning. Okay. So now, how can you represent your source? What is the electrical circuit diagram of the representation of the representation of EMF? You see, suppose, so this is the EMF value is E, this the terminal is A, this terminal is B. So this is the representation of ideal source. That means internal resistance is 0. For practical source, we can write, you see, this is E, the internal resistance is R, this is A terminal, this is B terminal. So in this way, you can represent the practical source. So this is practical source. Real source. In the real source, there is internal resistance. So now that can be written as also like this. This is A terminal, this is B terminal, this is R, this is E. The whole this is your source. So here the internal resistance is taken outside for easy looking. Or you can say this side, you can shift the internal resistance to right side also, no problem. So this is the representation of a practical source. Then what is voltmeter? So now you see what is voltmeter. Voltmeter is an electrical device which measures the potential difference across any two terminals. And resistance of voltmeter is very high. It tends to infinite. Ideally, the resistance of the voltmeter is taken to be infinite. And voltmeter is always connected in parallel across the load. Suppose you see, let us take an example. This is A terminal, this is B terminal. This is a battery of EMF 10 volt. The internal resistance is 0.1. And here AB terminal is connected to a load. That load is R. That is 4.9 ohm. What do you mean by load? Load is that which consumes some energy. So here electrical load is R. That is 4.9 ohm. So here tell me what is the current here? What is the current in the circuit? So I is equal to EMF divided by R plus R. That is 10 volt by R is equal to 0.1 plus R is equal to 4.9, that is equal to 2 ampere. This is the current. Okay. So here current is equal to 2 ampere. Now I want to find the voltage across A and B. So VAB is nothing but IAB into RAB. You know V is equal to IR. So VAB is equal to IAB into RAB. I is equal to 2 ampere. Resistance is equal to 4.9. So if you multiply, you will get 9.8 volt. And that 9.8 volt will be measured by what? Measured by the voltmeter. If I will connect a voltmeter like this, so voltmeter is always connected in parallel with the load. Okay. So here why it is connected in parallel? Since the resistance of the voltmeter is infinite, so no current. That means without voltmeter, what was the current? 2 ampere. With voltmeter, what will be the current? Because this is infinite, so no current will pass through this. So the current will be again 2 ampere. That is why voltmeter is always connected in parallel. But if I will connect voltmeter in series, what will happen? In this problem, I will connect a voltmeter in series. What will happen? So same 10 volt, 0.1 ohm. This is your 4.9 ohm. So here resistance of the voltmeter is what? Ideally infinite. So what will be the current? Current is equal to voltage by all the resistance, that is 0.1 plus infinite plus 4.9. So that means 10 by, if you add infinite to any other things, so you will get infinite. So the current will be 0. So you are measuring the voltage, voltmeter, you are trying to measure the voltage across this, but here you see the load will be affected because the current through this will be 0. So that's why voltmeter is always connected in parallel. Then what is ammeter? Ammeter measures the current and it is always connected in the series. You see. So here this is, you see. So first, let us say this is ammeter and this is 10 volt. This is R is equal to 0.1 ohm. This is your 4.9 ohm. So this is your ammeter. Without connecting ammeter, what was the current? 2 ampere. If you connect ammeter, then the load current must be same. So here resistance of ammeter is very small, tends to 0. Ideally resistance of ammeter is 0. If resistance of ammeter is 0, then what is the current? Current is again 10 by 0.1 plus 4.9, that is 2 ampere. So the magnitude of the current remains same without connecting ammeter or with connecting the ammeter. But if you will connect the ammeter instead of in series, I will connect ammeter in parallel. What will happen? You see. If I will connect wrongly the ammeter in parallel with the load, so here resistance of the ammeter is 0. Let us say this is A point, this is B point. Then what is the equivalent resistance across A and B? This is 0, this is 4.9. So equivalent resistance across the, or you can say, equivalent resistance across A, B is equal to R1 into R2 by R1 plus R2. That is equal to 0. So if it is 0, then what is the net current? net current is equal to total voltage 10 divided by this 0.1 ohm plus the equivalent of these two resistance is 0, so you will get 100 ampere. You see, so 100 ampere current is too much. When this 100 ampere current will pass through the ammeter, so ammeter will burn. Okay, so that's why ammeter is never connected in parallel. Ammeter is always connected in series. Similarly, voltmeter is always connected in parallel. So voltmeter never connected in series. So now we will see what is the difference between open circuit and short circuit. Open circuit and short circuit. You see, suppose we will take same problem. This is A, this is B terminal, this is 10 volt, this is 0.1 ohm. Okay, so here and same circuit here, this is 0.1 ohm, this terminal is A, this terminal is B. So here AB terminal is open, but here AB terminal is, so suppose you see, I will connect a switch here, and this is your resistance. The load resistance is 4.9 ohm. Okay, so this is a switch. And here what happens? So AB was connected to 4.9 ohm. This circuit same. So here switch is open, here switch is closed. Now what will happen? So during open circuit condition, what is the current? Current is equal to 10 volt divided by this resistance 0.1, and it is open means there is air resistance is very large, infinite, plus 4.9. So what is the current? So during open circuit condition, current through the load is equal to 0. Okay. Now come to short circuit condition. What is short circuit condition? You see, so this A and B terminal was connected by a wire. That is called short circuit. So if it is short circuit, then every current, whatever the current will pass, that will pass through this. That will pass through this. That is called short circuit current. No current will pass through this. Because why? Because the resistance of this short circuit path is 0. If resistance is 0, then what is current? So current is equal to ISC. Short circuit current is equal to voltage 10 volt divided by total resistance 0.1 plus what is the resistance of this? So here resistance is 0, here resistance is 4.9. Two resistors are connected in parallel. So the equivalent resistance is 0 into 4.9 by 0 plus 4.9, that is 0. So that implied 100 ampere. So that means in open circuit case, the current is minimum. In short circuit condition, current is maximum. Now we will find the voltage across A and B. So voltage across A and B is equal to what? So here current is, so here voltage across A and B is equal to the total supplied voltage is what? That is E minus I into R. So here E is equal to 10 volt minus I. In the open circuit condition, current is 0. Internal resistance is 0.1. So the voltage is equal to 10 volt. But what is the voltage across short circuit condition? Across the short circuit condition, what is the voltage across this load? Here you see the current will pass through this. Current will pass through this. No current will pass through this. So here current through the AB resistor 4.9 is equal to 0. So I can say V is equal to I into R. So current through this load is 0 into resistance is 4.9. So voltage across AB is equal to 0. So that means in open circuit case, the terminal voltage is maximum, and in the short circuit condition, the terminal voltage is minimum. So this is the difference between open circuit and short circuit. In open circuit, current is minimum, voltage is maximum. In short circuit condition, current is maximum and voltage is minimum. Next, energy and power in electrical circuit. Energy and power in electrical circuit. So now see, suppose this is an element. This is an element. This element may be a load, resistor, may be a source, may be a battery. So this is an element. Okay. So let I is the current through the element. Then in dt time, so I is the current in the element. In dt time, the amount of charge passes through this element is equal to what? dq is equal to I into dt, because you know I is equal to dq by dt. So due to this is motion of the charge, due to the passage of charge dq, potential energy change. So for potential energy change for this amount of charge is equal to du, and you know the potential energy du is equal to v dq. So we are taking, suppose this is A terminal, this is B terminal, I am taking VAB into dq. You know that the potential difference between 2 points is the amount of work done by bringing a unity charge from one point to another. So here the potential energy is nothing but the work done is equal to V into dq. So that is equal to VAB into dq is nothing but I into dt. So this is the potential energy. And you know what is the rate of change of energy? That rate at which energy is transferred either into the circuit if it is a load or if it is a resistance, or out of the circuit if it is a source like a battery. So the rate of energy is equal to du by dt, which is equal to VAB into I into dt by dt, that is equal to VAB into I. So this rate of energy is nothing but power. So you can write power is the product of voltage into current. Okay, or simply P is equal to V into I. P is equal to V into I. Then what is the unit of power? What is the unit of power? Power is equal to voltage into current. Voltage is equal to what? The unit of voltage is volt. Volt is nothing but joule per coulomb. And I, current is nothing but coulomb per second. Coulomb cancel. Joule per second is equal to watt. So this is the unit of power. Okay. So now you see, now we'll discuss the power input to a pure resistor. If this element is a resistor of resistance value R and current passing through it is I, then what is the electrical power? What is the electrical power delivered to the resistor? So electrical power delivered to the resistor is equal to, suppose this is A terminal, this is B terminal, that is VAB, potential difference into current. That is equal to VAB is nothing but I into R into I. So that is equal to power is equal to I square by R. Again I can say I is equal to what? V by R whole square into R. That is V square by R. So we can say power is product of voltage into current, or I square into R, or V square by R. Any formula we can use. So what happens when current passes through a resistor? What happens? So this current means moving charge. So when moving charge collide with atoms in the resistor and transfer some of the energy to the atom, by which its internal energy increases. If internal energy increases, temperature will increase. Temperature increase means heat is produced, and that heat will radiate to the surrounding, which is treated as loss, of energy. Or we can say energy is dissipated in the resistor at a rate I square R. So when current passes through any resistor, that due to that current, some energy is lost in the form of heat we can say that energy is energy loss due to dissipation. Okay, energy is dissipated in the resistor at a rate what? I square R. So that is why every resistor has a power rating. That means suppose this is a resistor whose power rating is 5 watt. That means if the current passes through this resistor and it can maximum produce 5 watt. If the current value is more, what will happen? The heat produced will be more. So due to that, the resistor will damage. Next, power output. Next, power output of a source. Power output of a source. Suppose this is a battery. Okay, this is a battery. Battery has two terminals. One is positive, another is negative. So this positive terminal is connected to a light, headlight. Suppose this is the headlight of your car. Headlight of the car. And this is the battery of your car. So here battery is connected to the headlight. Okay. So here energy is energy delivered to the external circuit. This is the external circuit. This headlight has a some coil. That coil has a resistance, let us say R. Okay. So here I can write in this way. So this is the positive terminal of the battery. This is the negative terminal of the battery. It is connected to what? A headlight, that is resistance R. So here current will start from positive terminal and it will end in the negative terminal. But inside the electrolyte, the direction of the current is from lower to higher potential. Okay. So what is the energy delivered to external circuit? Energy delivered to external circuit by whom? By the source is equal to P is equal to V into I. Okay, let us say this is A point, this is B point. So voltage across the terminal is VAB into I. So that is nothing but I square R. So that is equal to, but we know what is VAB. But we know VAB is equal to E minus IR. The voltage across this battery, that is output voltage across the battery, is the maximum voltage E minus the internal drop. So that implied power is equal to V into I. In place of V, you write E minus IR. Okay, into I. That is equal to E into I minus I square into R. So this is the net output power across the load. Then what is EI? EI is nothing but the rate at which work is done by which force? Non-electrostatic force inside the battery, or it is called maximum power delivered by the battery. And what is I square R? It is the power loss. Or you can say it is the energy dissipated inside in the internal resistance. This is the energy dissipated. So let us say the 100 watt is the maximum power given by the battery. Out of that 10 watt is internal loss. So 100 minus 10, that is 90 watt is available across the load. So that is called net output power. Or you can say the net output power is equal to, here current is I, so I square R. So that means I square R is nothing but EI minus I square R. So this is the equation we have to use when we will solve some problem. See, power input to a source. Suppose this is your car battery. Okay, the battery of the car. So it is used to charge this battery. That means in the car there is an alternator, there is a voltage generator. So that generator is connected to the terminal of the battery. So here there is a charging process. That means this alternator, which you can say it is a generator, which delivers the power, and that power or that energy is absorbed by the battery of the car. So here power input to a source. So here power is absorbed by the battery. Battery is absorbing power from this source. So that means here V is greater than EMF of the battery, because this must be greater than this E. So here what is the difference? Since V is greater than E, that means V is equal to some E plus some drop. So drop is equal to IR. So V is equal to E plus IR. Then what is the power absorbed by this battery? Power absorbed by this battery, or rate of energy absorbed by the battery, is called power. So power is nothing but the terminal potential difference into I. So VAB is nothing but E plus IR into I. So that is equal to EI plus I square R. So here battery is absorbing power. If it is absorbing power, then current direction is from positive terminal to negative direction. But if the battery will deliver the current, direction of the current is from negative to positive. Okay, so for delivering the power, direction of the current inside the battery is from lower to higher potential, and when the battery will absorb the power, direction of the current is from higher to lower potential. Okay, so now see the total power given by the source will help to charge this battery. Okay, so now out of total power, this power is converted from electrical to chemical energy. And this I square R is a loss in the form of heat energy. So you see, when you are charging the battery, this power EI will help to convert electrical to chemical. After charging, what will happen? So whatever the chemical energy is there, when it is used to an external circuit R, it will now deliver, it will convert chemical energy to electrical energy. Okay, so here one thing happens. So during charging of a battery, this I square R, this power is wasted in the form of heat energy. Have you marked when you are charging the battery of your computer, at that time the computer will be hot. Why? Due to this I square R component. Okay, so if you will charge the battery frequently, this heat can damage, or this heat produce will the slow the lifespan of the computer. Okay, so with this, though the subject it was very easy subject, but the concept of EMF is actually somewhat difficult. So if you are interested, you can skip that video and you just know what is the terminal potential difference, what is EMF, what is internal drop, what is the total power given by the source, what is I square R loss.